Thank you. Thank you. Okay, so in section 5.1, we had some fundamental identities. And see if you can fill in the blank. Suppose you see the cosine of x divided by the sine of x. Does that make you think of another trig function? Say loud. Cotangent, exactly. That's a fundamental identity. All of our ratios of our trig functions. So this one would be the cotangent. And what is the ratio for the tangent of x? That is the sine over the cosine. Good. What do you know about the cosine of minus x? Your choices are either it's the same as minus cosine of x or positive cosine of x. So think about how the cosine, say, of negative pi over 4 compares to the cosine of pi over 4. They're the same. Cosine was an even function. This is the even function identity. The cosine of minus x is the same as the cosine of x. Now, how does the sine of minus pi over 4 compare to the sine of pi over 4? Sine of minus pi over 4 compared to the sine of pi over 4. They're opposite in sign, aren't they? So that's the odd function identity, that the sine of minus x is minus sine of x. Only the cosine and 1 over the cosine are considered even functions. In that putting the minus angle in here is the same as putting the positive version of the angle in here. All of the other ones change the sign because they have some sine function in them. Okay, do you recognize this identity? Right here. It is, so what goes in the blank? 1. Sine squared plus cosine squared is 1. And so if I wanted to know what 1 minus the cosine squared of x is, what would you tell me? I just took that identity above and rearranged it. I kept the cosines, I took the cosine squared to the other side by subtracting. So 1 minus cosine squared will be the sine squared. So you need to know this Pythagorean identity in its 3 equivalent forms. Sine squared plus cosine squared is 1. 1 minus cosine squared is sine squared. 1 minus sine squared is cosine squared. Then we have a version of it with tangents. Tangent squared plus 1 is equal to what? Well, let's just go back here and derive it. To go from a sine squared to the tangent squared, you divide by cosine squared. So divide all 3 of these terms by cosine squared, and then tell me what goes in this blank over here. Secant, right? If I'm dividing by cosine squared, that'll give me a tangent squared. That'll give me plus 1, and 1 over cosine squared is secant squared. And if I want to rearrange that, I can also say that secant squared of x minus 1 is equal to tangent squared. Okay, so here in this example, I want you to write this expression. Write the secant of x minus the cosine of x as a product of two trig functions. Right now it's written as a difference, and I want you to write it as a product. So let's start with that difference, and let's write everything in terms of sines and cosines. So let's start with this, secant of x minus the cosine of x, and let's replace the secant of x with its equivalent expression in terms of sines or cosines. What is the secant of x equal to? 1 over cosine. So I can say now I have 1 over the cosine of x minus the cosine of x. And I'm going to go ahead and do the subtraction. When you subtract two fractions, you need to get a common denominator. The common denominator between the cosine of x and 1 is going to be the cosine of x. So that means I need to multiply this second fraction by the cosine of x over the cosine of x. Okay, so I'm getting a common denominator. Now my two functions have a cosine on the bottom, so I'm going to write them as a single fraction. And so on top, I have a 1 here minus the product of two cosines. So let's write that as cosine squared of x. But what did we say 1 minus cosine squared was? That is sine squared. So I've written it as a quotient. Now I want to write that quotient as a product. So I'm going to think of sine squared as sine times sine. And I'm going to rewrite this as the sine of x times the sine of x over the cosine of x. Because I know an identity for the sine of x over the cosine of x. What is it? Tangent. And now I've got a product. It's the sine of x times the tangent of x. Yeah, when you multiply three things together or divide, a times b times c, it can be done in that order and then multiply by a, or it can be done in this order. That's called I don't know, what do you call it? Associative property of multiplication. So I'm grouping these two products together, and then I'm going to multiply it by that one. So we're going to play lots of games like that. We're going to take a given expression, apply some algebra and some fundamental identities to make it look like another expression. And that's where I'll pick it up in section 5.2. Everybody's got that. The chapter title is Verifying Trig Identities. So we're going to take a given expression and through a sequence of steps, transform it to another expression. These two expressions will be called identities because they're identically equal to one another, give or take some rearrangement of terms. So in my first example, I want you to verify that here's my first example, that when I multiply a tangent with a cosine, that I'm going to get a sine. And so the way we're going to do is we're going to pick the side of this equality here that has the most stuff going on. In my example, it's on the left. Then use some of the fundamental identities and whatever algebra skills I have and see if I can reduce it to simply a sine of an angle theta. Okay, so you work with just one side, do some steps, see if you can get the other side. So tell everybody what side you're starting with. And then you just start trying stuff. And so when I look at that, I think, well, I know that I don't want any tangents or cosines in here. Tangent can be written in terms of sine and cosine. So that's where I start. I'm going to replace tangent of theta with the sine of theta over the cosine of theta. And now I'm essentially done. How do I multiply those two together? Yeah, this is multiplying two fractions together. You most multiply straight across. But when you have a factor common in the denominator, as you do in the numerator, in a product, you can cancel it. So I cancel from here to here, and boom, I'm done. Okay. That was way too short, wasn't it? But it was like the stretching exercises when you go to the gym. You don't just go there and pick up a big old bunch of heavy weights. You got to get yourself loose first. So now let's increase the tension here on your machine. And let's go with the next one. Verify that you can take the product of the cotangent of theta with the sine of theta with the secant of theta. When you multiply those three things together, show everybody that you can get one. So that's the statement of the identity. And I want you to kind of go through the same sequence of steps. Rewrite the side that you're going to start with, and then start doing stuff to it. Okay. So we begin with cotangent of theta times the sine of theta times the secant of theta. And I had pretty good luck in the last example, just replacing everything with equivalent sines and cosines. So let's start with the cotangent. Cotangent is cosine of theta over the sine of theta. That's already in terms of sine, so let's just put it here. And what about the secant? Secant is 1 over cosine. And now I look at that, got the same deal that I had going on last time. I got a product, common factors top and bottom, I can cancel. And then we're done. Cancel, 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 cancel. So I'm left with 1 over 1. There's really no need to cancel the 1. I want to end up with a 1. Okay. All right, here's my next one. I'm going to give you a messier looking stuff. Let's see if we can take the cosine of theta, divide it by the sine squared of theta, then subtract the cosine of theta times the cotangent squared of theta. See if that difference can be rewritten strictly in terms of that single trig function. Cosine over sine squared minus cotangent squared times cosine is supposed to equal cosine.
Are these always going to be true?
Yeah, they're always going to be true. That's why they're called identities. They're identically equal to one another.
Can you tell us to find what is equal to?
Uh-huh.
You're not gonna trick us?
I'm not going to trick you. Ouch. Hey, you mean old witch, are you going to give us something that doesn't work? That's what you just said. In a more kind, gentle way. Okay, so let's write down the side that we want to start with. And then let me reiterate that what we've done in the last 2 problems worked twice. Writing things in terms of only sines and cosines. Hey, why don't we try that again? Let's keep everything in terms of sines and cosines, but let's rewrite the cotangent. This is cotangent squared. So just take the cotangent ratio. What is the cotangent ratio? Cosine over sine and square it. So I can replace cotangent squared with cosine squared over sine squared. So that's what I'm going to do right here. I'm going to replace cotangent squared with cosine squared over sine squared. All right, so now I'm going to do it. I'm going to go ahead and I've got a cosine out here times that. So when I multiply cosine with cosine squared, I'm going to get a cosine cubed. Keep this the same. But now I see I have 2 fractions with a common denominator. Let's put them together as a single fraction. And now I need maybe a suggestion from you guys. Say it again. Which one? Because? Can you, but we can't subtract like that. That's like taking x minus x cubed, right? Those are different order of terms. So I can't combine them and get it, say, an x squared. I'm going to, what if I had, say, an x minus an x cubed? Then I have a common factor of x. Well, here I have a common factor of cosine. So I'm going to pull out that common factor. And so when I do that, I'm going to have a 1 in this slot and a cosine squared here. And that makes me feel pretty good because we've seen mere seconds ago an expression that was equivalent to 1 minus cosine squared. That is sine squared. That's the rearranged version of our Pythagorean identity. So if that stuff in the parentheses is sine squared, I'll replace it. And there you go. I've got a product, common factor on the top and the bottom that I can cancel. And once I cancel it, I'm done. I've got my cosine of theta. Okay. It's just a little puzzle. Any questions? All good. How about y'all? If I look okay in there? Okay, I'm gonna flip the page. The next one we're going to do, number 4. Let's see if we can verify that when I take the sine of theta and divide it by 1 minus sine squared of theta. So I'm giving you something that's already written in terms of sines and cosines, and I want to see if you can write it as the product of the secant of theta with the tangent of theta. Put that dot there. Starting with the sine divided by 1 minus sine squared, see if there's some way to make that look like the product of a secant and a tangent. Yes?
Do you also always have to start with that side?
No, I can start on the right side. I can start with the secant times the tangent and see if I can make it look like the left side. That's why it's important for you to restate the side that you're starting with. I can start with this and make it look like that, or this and make it look like that. But just after you're given the problem, tell me what side you're starting with. I'm going to start with the left-hand side. Because when I look at that, I already see something that I want to do. What is it that I see? 1 minus sine squared is equal to cosine squared. So I'm going to replace the denominator with cosine squared. Now I'm thinking backwards. What's a secant? 1 over cosine and a tangent. So I'm going to write this cosine squared as a 1 over cosine times a sine over cosine. Right? If you multiply 2 fractions, you multiply straight across. So I just peeled it apart so that it fit my needs. 1 over cosine is the secant. Sine over the cosine is the tangent. And I'm done. Where? Where what? What, when, how, why, who? I saw this. This is kind of like peeking at the answer in the back of the book. I want to take my answer and make it do that. So I recognize cosine can be written as cosine times cosine. And sine can be written as 1 times sine.
I thought you were changing the right side, but I didn't know you were.
Nope, I'm starting with the left and making it look like the right.
That was real.
Okay, so right up here, I'm gonna start with the left-hand side. You could. You could. What if we'd done it? Let's go ahead and do it the other way. Another way. Let's start with the right-hand side. Yeah, but here there's probably the same amount of stuff, right? So I'm going to start with by writing down secant of theta times the tangent of theta. Then I see my answer doesn't have any secants or tangents, so now I'm going to convert these to sines and cosines. Secant is 1 over cosine. And the tangent is the sine over the cosine. Now I have a product and I'll just multiply straight across. 1 times sine will give me sine on the top. Cosine times cosine will give me cosine squared on the bottom. Then I'm trying to make it look like this. So my next step is just to replace the cosine squared. I know cosine squared is 1 minus sine squared. And then I'm done. So this side was just as easy to do. You take your pick which side you want to start with. But again, tell me what side you're starting with. Work only with that side until you get it to look like the other side. So when I was a kid, they always have those little mazes in game magazines. You can pick where you start and try to end up in the middle. Well, this is like starting in the middle and try to end up in one of the border doors. Exactly like that. We're doing little puzzles. I had no buttons as a kid. Well, when I was young. All right, so here's another one. I guess we're on number 5. I'm going to take 1 plus tangent of theta divided by 1 plus the cotangent of theta. And I want to see if I can make this equal to the tangent of theta. Take those two sums and see if I can simplify it far enough to get it to be the tangent.
So is the plus or minus 17 do with whether or not it's an odd or even function?
No, it has nothing to do with odd or even, it's just how it acts on an angle and the opposite of that angle. Okay, so this one's obvious that I need to start with the left-hand side, right? There's nothing to do over here, so let's start with this. One plus the tangent of theta over 1 plus the cotangent of theta. All right, what do you want me to do as my first step? Yes, sir. You cannot. You can only cancel through a product, not a sum. Once that plus sign's there, I can't just pick my favorite term and cancel it. How? How would you, I mean, what? If you have, say, 4 plus 9, that's 13, right? If I divide 13 by 4, that's different than, say, canceling the 4s and getting 10. Right? Can't do that because 4 plus 9, that little dividing bar acts as parentheses. And we can't cancel through a sum. We can only cancel through a product. Yes. That's exactly the way we're going to start. Okay. So be careful. You can't do this. Can't just cancel and say that that's 10 because it ain't. Okay, don't cancel through a sum. So we've got to try to make this look like a product. First thing we're going to do is replace tangent with sine over cosine, replace cotangent with cosine over sine. But I still have sums. I have a sum on top and a sum on the bottom. If I want to combine those, I've got to get a common denominator. So in order to add this one to that fraction, I got to think of this one as being cosine theta over cosine theta. In order to add these two guys together, I'm going to think of this one as being the sine theta over the sine of theta. So we're getting a common denominator now. Because that's in the denominator. So I'm getting a common denominator right there. Now I'm going to get a common denominator right here. Now that I have the common denominator, I'm going to go ahead and write that on the top as a single fraction. Cosine of theta plus sine, all divided by cosine of theta. And I'm going to write the bottom as sine of theta plus cosine. Oops, I wanted a cosine there, didn't I? That was kind of stupid. This was a sine. Here we go. That helps. There we go. Now I have a common denominator. Now I can add those and write that as a single fraction. So it'll look like this. On top, I'm going to have cosine plus sine all over cosine. Downstairs, I'm going to do the same bit. I'm going to have the sine plus cosine all over the sine. I'll even put it in parentheses so you can see what I did in putting those fractions together. So I've got a kind of a compound fraction. I've got one fraction divided by another. How do we do that when we have numbers as our fractions? Flip the one on the bottom over and multiply. So now we're going to do the flip and multiply step. So let me take it up here. I'm going to keep the fraction the way it is on the top. And I'm going to take the one on the bottom and flip it over and now make a multiplication problem out of it. That's right. Cosine plus sine is the same as sine plus cosine. The order of addition doesn't matter. So I have a factor that's common on the top and the bottom, and I can cancel them. Cancel the common factors. And we're left with sine of theta on the top and cosine of theta on the bottom. Hey, I know what that is. That's the tangent of theta. And that's what we were trying to do. Okay. So a lot of times when you convert things to sines and cosines and just do what the expression asks you to do, you end up with what you need. So you have to do it correctly, right? You gotta add by getting a common denominator. Cancel only through a product, that kind of thing. You want another? Good answer. That was number 5. I got a number 6 for you. I got all the way through number 11. So act like you enjoy this, dang it. Number 6. Oh my, we got all kinds of squared stuff together. I'm going to take a secant squared, multiply with a cosecant squared. And see if I can transform that into a secant squared plus a cosecant squared. Isn't that interesting? The product of a secant squared and a cosecant is the same as a sum of a secant squared and a cosecant. That's very interesting. Yes.
So when you ask us to verify Not necessarily, so like sometimes they're gonna be wrong, right?
No, verify means that they're true. Verify this is an identity. So verify that it's an identity.
Okay.
Verify that x squared plus 2x plus 3.
So they're all, like, they'll always
I
have.
don't
to be
know.
right.
I don't know what that's equal to. Right. Sir,
Does this mean that c squared is 2 and opposed to the squared is also 2?
that's an example of a pair that would do that, right? 2 squared times 2 squared is the same as 2 squared plus 2 squared? No, it's not, is it? 2 squared is 4. 4 times 4 is 16. 16 is not the same as 4 plus 4.
So the sum of secant squared. That was
Oh, secant squared itself was a 2. Because, so they're each square root of 2. Sure. This is an example, though, where I think if I start on the right-hand side and manipulate it might be easier than starting on the left-hand side to get the right-hand side. Because I've seen how to add things. I add things by getting the common denominator. Not much interesting can happen when you multiply it. So I'm going to start with the right-hand side and try to mess with it. Let's copy down the right-hand side, write things in terms of sines and cosines, and then let's take it from there. So I'm going to start with the right-hand side. And then I'm going to write those in terms of sines and cosines. So secant is 1 over which trig function? So secant squared will be 1 over cosine squared. Cosecant squared then is 1 over sine squared. Now I'm adding 2 fractions. These 2 fractions have different denominators, so I can't add them until they have a common denominator. What's the common denominator going to be? Yeah, just the product of these 2. So I've got to multiply this fraction by sine squared over sine squared, and this one by cosine squared over cosine squared. So here I'm going to get a common denominator. So I'm going to take that first fraction and multiply it by sine squared over sine squared. I'm going to take that second fraction and multiply it by cosine squared over cosine squared. So now both of them have a sine squared times a cosine squared in them. So I'm going to write them as a single fraction. And up here, I'm going to have sine squared times 1, which is just sine squared, plus 1 times cosine squared is cosine squared. Okay, so you're probably thinking, right? We started here, and we're going to make it look like this. So we're almost there. What do you see in my numerator? That's 1. Sine squared plus cosine squared is 1. So now I've gotten rid of a sum. I want it to look like this. So let me write it in the reverse order. Secant squared is 1 over cosine squared. Well, here's my 1 over cosine squared. And here's my 1 over sine squared. And they are indeed multiplied. So I split this product apart as the product of 2 separate fractions, and then I replace them with their reciprocal identities. And we did it. We made the sum into the product. Okay. Let's amp up the level of difficulty here. Claim here is that the tan squared of x divided by the secant squared of x is the same as 1 minus the cosine of x times 1 plus the cosine of x. Tell me a side you want to start with. Left or right? Start with the left? Let's do it. What would you do first? Right, in terms of sine and cosine. Seems to be a good method of attack. Okay, so tangent squared is sine squared over cosine squared? What about secant squared? It's 1 over cosine squared. What next? Flip and multiply. You're dividing this fraction by this fraction. So keep this one here, flip that one over and multiply. Okay, I got a common factor, top and bottom. I'm gonna take it out. And I have sine squared over 1, which is just sine squared of x. I'm trying to write that in terms of cosines. So now I need to replace my sine squared with what? 1 minus cosine squared. Now what? Look at what I have and look at what's we're trying to get. Close. I'm going to use this idea. The difference between squares is something that can be factored. A squared minus b squared factors how? A minus b times a plus b, and that's what we have above. Difference of squares. So I should be able to factor this as 1 minus cosine times 1 plus cosine. And that's what we got up there. And we're done. Okay, so changing things to sines and cosines and then doing the algebra that presents itself has been working pretty well for us. And then the closer we get, we kind of eyeball what we're working toward and then manipulate that in that direction. All right, let me see if the next one's too long to put right here. That was 7. Ah, number 8 has kind of a trick to it. What page number am I on? 1, 2, 3. That was page 4. How about a page 5 for you? Problem number 8. Problem number 8 says that if you divide the sine of x by 1 minus the cosine of x, I did? If you divide a sine of x by what? Come back here. By 1 minus the cosine of x, you should get the same thing as if you take a 1 plus the cosine of x and divide it by a sine of x. Pick a side, any side. Which one you want to start with, left or right? Oh, I heard both answers. Start with the left. Let's start with the left. Well, we've already gotten things written in terms of sine and cosine. So I don't have that available to me. I can't split up that into two fractions because they both, it's a 1 minus cosine of x stays together. So the only other thing that's allowed in every state, maybe not Arkansas, is that you can take any fraction and multiply it by 1. So I can multiply this by 1 in any form that I want. If I wanted to multiply it by 5 over 5, that's 1. But I see I've got a sign in the denominator over there. How about I multiply top and bottom of this thing by sine of x over the sine of x? Because at least it'll put the sign in the denominator for me. Okay. So it's going to give me a sine squared of x on top. I'm going to keep the denominator factored because I want to keep my sine of x separated. So I'm going to go ahead and write that as the sine squared of x over the product of 1 minus the cosine of x times the sine of x. So now I'm looking at my expression up here and I don't have any sign on the top. So I'm going to make a replacement for the sine squared of x. What am I going to put in for sine squared of x? 1 minus cosine squared. Now, do you see anything you could do?
Get rid of the 1 minus square.
We've got the difference of squares again. A squared minus b squared is on top. And it should factor into a minus b times a plus b. Factor this numerator as the difference of squares. 1 minus cosine times 1 plus cosine. That's why I left the bottom factored. My goal was to eventually cancel, and I can see in the next step I can cancel. I got everything written as a product. So I've got that common factor of 1 minus cosine of x on the top and the bottom. I can cancel it. And we're done. And you see, if I started with this side, I'd have done kind of the same deal. I would have seen a sign here and I see I want cosines. So I would multiply top and bottom by the sine of x. Replace the sine squared with 1 minus cosine squared. Factor is the difference of squares.
On the left side, can't you like flip them over and like change the signs? And then since sine of x is equal to 1 minus sine of x, then
Well, I got lost.
okay, so like if you take them and then flip them and then change the signs, and then you do, and so then you have.
Flipping doesn't change a sign. Flipping changes the sign on an exponent, but it doesn't change the sign in a sum. Changes the sign in an exponent. Yes.
On the test, are we gonna have to show like right off the side like sine of x and then sine over x when we multiply it, or can we just skip that step and just write out after we multiply? We have to show our work for that.
Well, I guess it's pretty obvious. I don't know. Don't you get pissed off when I skip steps? Part of verifying is showing the world how to get from one thing to the other, right? If I had to show you how to bake a cake, you'd want to see all the stuff before, not just me opening the oven and say, ta-da, there's a cake. All right, let's go to number 9. Number 9, we want to take the secant of x minus the tangent of x, put it in parentheses and square it. Secant of x minus the tangent of x, all squared. And that, my dear friends, can be rewritten as 1 minus the sine of x divided by 1 plus the sine of x. That looks like somebody just made something up. That doesn't look true to me at all. But it is. We have had success in taking things that were not sines and cosines and starting there and making them look like sines and cosines. So I vote we start with the left-hand side. So let's go ahead and make them into sines and cosines. Secant is 1 over the cosine, tangent is the sine over the cosine. And in the parentheses, I have 2 fractions with a common denominator. I'm going to write them now as a single fraction over that cosine of x. So I'm going to have 1 minus the sine of x divided by the cosine of x. All of that is to be squared. When you square a fraction, you square the top and you square the bottom. So I'm going to write that now. I'm going to write that as 1 minus sine of x all squared divided by the cosine of x squared, which I write like that. Squaring a fraction means you square the top and square the bottom. Now, I don't want to multiply the top out because look what I'm trying to end up with. I'm trying to end up with a 1 minus sine of x. I happen to have a pair of them, but I'm going to keep it factored. Instead, I'm going to replace the cosine squared. Cosine squared can be written as what? 1 minus sine squared. Cosine squared is 1 minus sine squared. The bottom is the difference of squares. The bottom is an a squared minus b squared expression. That should factor a minus b times a plus b. I should be able to factor that as a 1 minus sine of x times a 1 plus sine of x. Did that jump out at you? Then let's do it. All right, tell me what to do next.
Since you've got 2 with the 1 minus sine x, can you separate those ones?
Yep, 1 minus sine of x squared means I've got a 1 minus sine of x times a 1 minus sine of x. So I've got a common factor. So I can cancel one of these with one of those. So now there's only one of them on top, and that's all we needed. We got a 1 minus sine of x on top and a 1 plus the sine of x on the bottom. So one of the things we've seen again is replacing things in sines and cosines helps. But also, we've had that Pythagorean identity pop up a few times. Sine squared is 1 minus cosine squared, or cosine squared is 1 minus sine squared, and that can be factored as the difference of squares. You look like a talented group of individuals who loves the operation of squaring. I bet nobody's ever said that to you before. Yes.
That last step that we did is the same as like when we used to do it's like 1 minus 16 squared.
Right, right. All right, so like I said, you guys are saying, I want to take an expression and I want to square it. Well, okay, I'm going to give you two of them. I want you to take the expression 2 sine of theta plus the cosine of theta, square it, then add it to 2 cosine of theta minus the sine of theta, square that, combine like terms, and show me that all you end up with is 5.
I don't have space for that. Can we make it bigger?
It ain't 0, it's 5. So you're gonna do it. You're gonna take the left-hand side and you're gonna square those bad boys, combine like terms and get 5. But you gotta remember that if you have, say, a plus b all squared, it's not a squared plus b squared. You can't distribute this power in here. Right? That can't just go there and you're done. How do you square a binomial? You multiply it by itself and then FOIL it out. So that's what you're going to do. So let's start with the left-hand side.
What would we do if we started with the right-hand side?
You'd be SOL, I think. There's nothing to do if you start with the right-hand side. You'd have to be pretty darn clever.
Can you, theoretically speaking, like subtract one of the, like the 2 cosine minus sine squared and put it on the opposite side? So it's
And
5
then-
minus. and
That
then-
looks more fun?
Well, no, I was just asking, like, can you do that with them as well? Like,
Yeah, I don't see why not. I just think why, it sounds like you're making your own problem. Why not use the problem I gave you? So what I'm telling you is you're going to square this by multiplying this stuff by itself. So you're right, you need a big old line here. You're going to take 2 sine theta plus cosine theta and multiply it with itself. Then you can do the same deal with that. You're going to take 2 cosine theta minus sine of theta and multiply it with itself. Just barely fit. I'm going to give you a minute to do it. I want you to FOIL those out. First times first, outside times outside, inside times inside, last times last. Multiply it out. On your mark, get set, go. Like, what do you get when you take 2 sine of theta and multiply it with 2 sine of theta? 4 sine squared theta. We got you started. Keep going. First, outside, outside, inside, inside, last. Well, both are back, you're gonna have a string of 8 terms. We'll see if any of them look alike. Don't peek, I'm gonna multiply mine out, then we'll compare. The peeking. Okay, I'll let you peek now. All I did was I multiplied this first one out. 2 sine theta times 2 sine theta gave me the 4 sine squared theta. Then 2 sine theta times the cosine theta gives me just that, 2 sine theta times cosine theta. Now the insides look like a cosine theta times 2 sine theta. I just put it in that same order as the previous term, 2 sine cosine. And then finally cosine times cosine gave me a cosine squared. So now I'm going to do it with this batch on the back. I still got the plus sign in between. I get a 4 cosine squared theta minus 2 sine theta cosine theta. Then the inside gives me another minus 2 sine theta cosine theta. And then the 2 last terms, I've got a minus sign times a minus sign gives me a positive sine squared. So there are my 8 terms of multiplying both of those binomials out. Let's see what it looks like. I have a sine squared term here and a sine squared term there. 4 of them added to 1 of them to give me a 5 sine squared. I have 2 sine theta cosine theta plus another 2 sine theta cosine theta. So now I got 4 of them. But look here, here's minus 4 of them. So that adds to 0. And then finally, the remaining terms are a 4 cosine squared plus a cosine squared to give me a 5 cosine squared. So we multiplied it out, combined like terms, and that's all that's left. And if I can get that 5 out of the way, I'll have a sine squared plus a cosine squared. That 5 is a common factor. I'm going to pull it out. And then sine squared plus cosine squared is 1. Did you have a question?
Yeah, you wrote minus 2 sine, sine, cosine, minus 2 sine, wouldn't it be 2 cosine, minus, or minus 2 cosine, cosine?
Where are we looking?
When you were getting your second,
That one.
yeah, when you were getting your second trinomial though,
Okay.
you wrote it as 4 cosine squared minus 2 sine.
There.
Times
So I
cosine.
took that times that,
Yeah, wouldn't that be minus 2 cosine times sine?
but it doesn't matter the order that I write it. 3 times 4 is the same as 4 times 3. Sine times cosine is the same as cosine times sine. Okay? That's the commutative property of multiplication. So I was just trying to saw what I got the first time I multiplied. I knew what was going to happen, so I tried to write them in the same order. Okay? Me and my stick here. This is when I have to surrender. No more, no more.
We need some of those too.
But you don't have one, so I get to give you more. I said I had 11 problems for you. And look, I'm on problem 10. Can we do it? Can we do it? Do you have it in you? We got 6 minutes. We have the 6-minute drill. I want you to take these two fractions here, 1 over 1 minus cosine of x, 1 over 1 plus the cosine of x. I want you to get a common denominator and add them, then simplify and see if you can simplify this all the way down to 2 times the cosecant squared of x. We're adding 2 fractions, so you need a common denominator. When you get that common denominator, magic happens, and it turns into 2 cosecant squared x. You just have to write it. What's the common denominator between 1 minus cosine of x and 1 plus cosine of x? That's right. It's just the product of those two. So let me write this fraction down. I'm going to leave a little gap there so I can put in my common denominator term. So right in here, I'm going to put in 1 plus the cosine of x over 1 plus the cosine of x. And over here, I'm going to put in 1 minus the cosine of x over 1 minus the cosine of x. Now they have the same denominator, so I can write their numerators all over that same denominator. So there's the common denominator. 1 times that gives me just that. The parentheses are doing nothing for me. So I'm going to bag the parentheses here. Same deal here. 1 times that just gives me 1 minus cosine with this plus sign. And I have my numerator over the common denominator. And then the cosine of x on top minus the cosine of x on top adds to 0. So I just have 1 plus 1 is 2. Now I think it's time to multiply out the bottom. I have a 1 minus cosine times a 1 plus cosine. And when you FOIL that out, what will you end up with? Only 1 minus cosine squared. The inside terms are going to add each other out. So this becomes a 1 minus cosine squared when we multiply them together. Quick, quick, what is 1 minus cosine squared? Hoorah. So I have 2 over sine squared. The 2, that minus that is 0. 1 plus 1 is 2. Can I multiply what by itself? I'm done because I'm trying to make that into a cosecant squared and I have a 1 over sine squared. My 1 over sine squared is cosecant squared. We're done. I can only spell cosecant. We are done. Okay. With 2 minutes to spare. So it's kind of hard to do this kind of thing on a web work, but there are some web works for you. But what I suggest is that you also try the problems out of the book. Okay. What page? I am on, there's a whole bunch of problems on page 209. That'll work.
So you said you're putting midterm, so not for anyone else.
I'm only gonna do the ones, I get this, page in Raider Link, and it only has the names of people for which I'm required to submit grades.
And is freshman like people who don't have credits or like if you had
That's a good question.
because they told me like they put midterm grades, but it doesn't show up for me, so I don't know if
It may be because might be it.
it doesn't apply.
But if you send me an email, I can tell you exactly where you stand.
Okay.
Professor, I have some questions on a couple of the problems.
Okay.
So on number 10, the one before the last one,